Sì. Allora cominciamo con le esperienze, giusto? Buonasera a tutti, benvenuti nel Dipartimento di Fisica. Io sono il direttore del Dipartimento. Siamo molto contenti di avere così tante persone qui in questa occasione così particolare. Cominciamo il pomeriggio di oggi con delle esperienze dimostrative sulle onde, sull'interferenza, perché quello di cui poi parlerà il professor Barry Barish sarà appunto un particolare tipo di onde, le onde gravitazionali, un risultato importantissimo, uno dei più importanti degli ultimi decenni, che come tutti sapete ha portato al conferimento del premio Nobel al professor Barish e altri due scienziati nel 2017 riguardo alla scoperta delle onde gravitazionali. Io adesso do la parola al professor Organtini che organizza queste esperienze.
Grazie. Io cercherò di sottrarre meno tempo possibile al professor Barish e quindi assumo che tutti abbiano almeno una vaga idea di che cosa sia un'onda, anche se non è molto precisa, non è importante, e quindi farò degli esperimenti per dimostrare alcune delle proprietà delle onde che si usano poi per fare queste misure sulle onde gravitazionali. Per fare questi esperimenti useremo due tipi di onde, le onde sonore e le onde luminose. Che il suono sia un'onda è stato dimostrato da Galilei, che in un esperimento fa suonare un bicchiere passandoci sopra il dito, sfregando il bordo del bicchiere, e osserva le onde che si propagano sull'acqua all'interno, e mettendo il bicchiere all'interno di una vasca piena d'acqua osserva anche le onde che si propagano all'esterno. Noi oggi non abbiamo bisogno di fare esperimenti così delicati, tutto sommato è molto difficile osservare queste onde. Possiamo usare uno strumento che abbiamo tutti nelle nostre tasche, uno smartphone. Basta scaricare un'applicazione che è stata sviluppata da fisici dell'Università di Aachen, che si chiama phyphox, che permette di usare i sensori che si trovano all'interno di uno smartphone per fare misure di fisica. Uno dei sensori che sono a bordo di uno smartphone certamente è il microfono, che serve per poter parlare al telefono naturalmente. Allora voi dovete immaginare un microfono come costituito da due lastre separate da una molla. Quando arriva un'onda sonora una delle due lastre viene compressa e oscilla rispetto all'altra, quindi misurando la distanza tra una lastra e l'altra si può osservare con gli occhi un'onda sonora. Quindi quello che adesso facciamo è osservare questa onda sonora. Come vedete sullo schermo io ho già attivato l'applicazione e quello che posso fare, ecco, sì, questo è il reminder, ho già attivato l'applicazione e quello che farò ora è percuotere un diapason e osserveremo la forma d'onda di questo diapason. La risoluzione dello schermo non è ottimale, però si capisce che c'è una forma d'onda sinusoidale. Possiamo cercare di vedere meglio questa cosa riducendo leggermente il tempo che mettiamo, che osserviamo. Ecco, adesso si vede molto meglio che c'è questa forma sinusoidale, ok? Uno dei fenomeni a cui le onde danno luogo è il fenomeno dell'interferenza. L'interferenza consiste nel fatto che due o più onde, quando arrivano nello stesso punto, possono sommarsi, e questa somma può avvenire in maniera costruttiva se le onde arrivano in fase l'una con l'altra, cioè arrivano con la stessa tutte e due in crescendo, tutte e due decrescendo nello stesso istante, oppure può avvenire in maniera distruttiva se un'onda è crescente mentre l'altra è decrescente, e questi due movimenti vanno insieme, in sincrono. Quello che succede è che l'onda si cancella completamente. Ora, se io percuoto quindi due diapason, i due diapason che hanno la stessa frequenza produrranno ciascuno un'onda con le stesse caratteristiche e queste onde si sommano tra di loro dando luogo ad un'onda che avrà ampiezza doppia rispetto a quella di un singolo diapason. Questo lo possiamo vedere sempre con Phi-Fox. Vedete che l'onda aumenta di ampiezza quando io li percuoto in due. Ok? Se invece i due diapason non oscillano alla stessa frequenza, ma oscillano a frequenze leggermente diverse, quello che succede è che si produce un'onda che ha una frequenza che è la media delle due frequenze dei due diapason, però l'ampiezza cambia perché in certi momenti si ha ampia interferenza costruttiva e in certi altri si ha interferenza distruttiva. Osservate la forma d'onda e vedete, se percepite anche con le orecchie questo tremolio che è dovuto al fatto che l'ampiezza dell'onda sta aumentando e diminuendo costantemente. Ora, questo fenomeno può essere sfruttato in molti modi. Uno di questi è quello che consiste nell'utilizzare questo fenomeno dell'interferenza insieme ad un altro fenomeno che è la diffrazione, che vi faccio vedere con questa figura. La diffrazione consiste nel fatto che delle onde piane che arrivano su uno schermo, in presenza di un'apertura su questo schermo, naturalmente attraversano l'apertura dalla parte dove possono attraversarla, e però facendo questo si cambia completamente la forma d'onda del fronte d'onda. In particolare qui vedete una foto tratta da Google Maps in cui si vedono le onde del mare che vanno verso la riva e poi arrivano su una diga foranea dove vengono fermate, però una piccola parte riesce a passare dall'altra parte e l'onda si apre a ventaglio e quindi si propaga in tutte le direzioni provocando quel fronte d'onda semicircolare. Naturalmente se avete più di uno di questi fronti d'onda, come può accadere in questo caso, quello che può succedere è che queste onde avanzano tutte in sincrono e se le onde si incrociano in qualche punto si può ottenere il fenomeno dell'interferenza insieme a quello della diffrazione. Ora, quello che si può vedere anche sperimentalmente, sia matematicamente che sperimentalmente, è che questo fenomeno della diffrazione è molto particolare e lo possiamo osservare in questo caso con un'applicazione che è il cosiddetto ondoscopio. L'ondoscopio è questo strumento che adesso vado ad attivare e poi vi proietto anche sullo schermo. Non ce l'ho più. Eccolo qua, eccolo qui. Ecco. Allora, quello che vedete su questo dispositivo è che, fatemi spegnere un'altra luce, no. È questa cosa, qui arrivano delle onde piane che io sto provocando sulla superficie dell'acqua che sta sulla vaschetta che sta lì sopra e qui ho messo uno schermo con due aperture. Queste due aperture lasciano passare dei fronti d'onda circolari che a certi angoli interferiscono negativamente, cioè ogni onda annulla l'altra onda e si vedono abbastanza chiaramente le direzioni in cui si ha interferenza costruttiva, per esempio in questa direzione, in questa direzione le onde si stanno sommando, però vedete che ci sono delle direzioni in cui le onde invece non si propagano, in questi punti qua, lungo queste direzioni, a questi angoli, l'acqua è ferma, non sta oscillando. e dalla misura dell'angolo a cui si formano i diversi raggi in cui c'è interferenza distruttiva si può risalire, conoscendo la distanza tra le due fenditure, a quella che si chiama la lunghezza d'onda di questa onda, cioè alla distanza che c'è tra due picchi consecutivi di quest'onda. Ora, questo fenomeno lo si può utilizzare in uno strumento che utilizza onde con una frequenza e con una lunghezza d'onda meglio molto più corta. Il fatto che la lunghezza d'onda sia molto più corta permette di avere questi angoli estremamente piccoli, abbastanza grandi quando la distanza tra le due fenditure è molto molto piccola, comparabile con quella della lunghezza d'onda. Questo fenomeno lo possiamo osservare con un altro strumento, che è quello che si chiama un interferometro di Michelson. Devi spegnere questo e vado invece a farvi vedere come funziona un interferometro di Michelson. Se lo trovo, eccolo qua, che è questo qui. Allora, questo è uno schema di un interferometro di Michelson. Se voi fate partire da una sorgente delle onde che si propagano in questa direzione e qui mettete uno specchio semitrasparente, una parte di queste onde attraversa lo specchio e una parte viene riflessa. Se qui mettete altri due specchi, una volta aggiunti sugli specchi, i raggi di luce, quindi di onde luminose in questo caso, vengono riflessi all'indietro. In questo caso questi raggi verdi tornano indietro di qua e vengono riflessi da questa parte dallo specchio. I raggi che invece sono stati prima riflessi, una volta che sono giunti su questo specchio, tornano indietro su quest'altro punto qua. E qui si sommano i raggi verdi con i raggi rossi, quindi quelli che hanno seguito un percorso e quelli che hanno seguito un altro percorso. Ora, quello che succede qui è che le onde luminose che arrivano in questo punto si sommano e quindi possono dar luogo a interferenza costruttiva e distruttiva, e a seconda dell'angolo al quale si trovano si può avere interferenza costruttiva o interferenza distruttiva. Naturalmente la distanza tra le bande nere e le bande chiare dipende dalla distanza che c'è tra gli specchi. Per esempio, se io riduco questo braccio, questa distanza tra questi due specchi, quello che succede è che cambia la distanza percorsa dai raggi verdi e quella percorsa dai raggi rossi. La stessa cosa succede se io cambio quest'altra distanza, vedete che cambia completamente la distanza tra i raggi riflessi da uno specchio e i raggi riflessi dall'altro. Su questo principio, come vedrete, si baserà un rivelatore di onde gravitazionali. Possiamo vedere questo strumento in funzione utilizzando un interferometro di Michelson che funziona con un laser che abbiamo qui, un laser rosso, che arriva su uno specchio semitrasparente, la luce viene riflessa da un altro specchio che si trova qui, torna indietro, arriva di nuovo sullo specchio e va a finire da quella parte. Contemporaneamente la luce del laser, arrivando sullo specchio semitrasparente, arriva su quello specchio lì, viene riflessa all'indietro e i due raggi di luce si fondono in questo punto, e quello che osserviamo lì è quella che si chiama una figura di interferenza. È circolare perché voi dovete immaginare quei due raggi poi orientati lungo tutte le possibili direzioni dello spazio, quindi quello che vedete è quella forma che vedete laggiù, che è una serie di circonferenze scure e una serie di circonferenze chiare. Le circonferenze chiare sono quelle dovute alla interferenza costruttiva delle onde dei due fasci di luce che stanno viaggiando all'interno dell'interferometro, che si sommano positivamente. Le frange scure invece sono dovute al fatto che i due raggi di luce hanno avuto un percorso diverso tale che le due onde si sommano cancellandosi a vicenda, e naturalmente ne vedete tutta una serie. Ora, misurando la distanza tra quelle frange scure si può capire di quanto si sono spostati gli specchi l'uno rispetto all'altro, e questo è uno strumento sensibilissimo. È sufficiente che io mi metto qui vicino e mi appoggio al tavolo, come vedete cambia la figura di interferenza che si riesce ad ottenere sullo schermo che si vede laggiù. Quindi è sufficiente che io mi appoggi al tavolo per produrre una inclinazione, una modifica del parallelismo tra gli specchi, e questo mi permette, cambia leggermente la distanza tra gli specchi. La cambio in maniera impercettibile, ma grazie a questo strumento io posso misurare e vedere, diciamo, questo fenomeno in maniera macroscopica. Ecco, diciamo, questo era sostanzialmente quello che volevo farvi vedere, diciamo, dal punto di vista sperimentale sulle onde, in modo tale che adesso il professor Barry Barish vi potrà illustrare il funzionamento di un interferometro per onde gravitazionali i cui principi di funzionamento sono gli stessi. So it's my pleasure to leave the stage to Professor Barry Barish, and please thank him.
Vi rubo ancora un paio di minuti, scusate, perché anche per fare un minimo di presentazione del professor Barish. Lasciatemi dire soltanto che oggi è anche l'occasione per inaugurare la Maldi Research Center. Che cos'è? È praticamente un centro dedicato alla figura del professor Amaldi, quest'aula prende il nome del professor Amaldi, che di fatto ha iniziato tanti anni fa la ricerca sulle onde gravitazionali. Il nostro dipartimento è risultato vincitore di un programma del MIUR per i dipartimenti di eccellenza, proprio con un progetto basato sulla ricerca teorica e sperimentale sulle onde gravitazionali e anche con dei contributi nel campo della fisica della materia e dell'ottica quantistica, per ragioni che sono legate, che spero risultino evidenti anche dalla presentazione del professor Barish. Allora, il professor Barish è un professore emerito della Università Caltech e ha naturalmente avuto un rilievo enorme nell'attività di ricerca in tutti questi anni, non solo nelle onde gravitazionali ma anche prima. Per esempio nel 1980 ha diretto l'esperimento macro nel Gran Sasso, è stato uno dei responsabili del cosiddetto GEM, Gammas, Electrons e Mons, che poi ha portato, ha condotto un esperimento che poi è stato portato avanti nel superconducting supercolliders. Poi è stato uno dei fondatori dell'esperimento LIGO, che è uno dei due esperimenti, l'altro è Virgo, che condotto anche in questo laboratorio, in questo dipartimento, scusate, dal professor Ricci e dal suo gruppo, esperimento che ha soprattutto il baricentro spostato in Europa, mentre l'AIGO è condotto in America. Sono i due esperimenti che poi hanno portato ai risultati di cui stiamo parlando. Ha avuto una serie di premi molto importanti, ma mi limito a citare soltanto il più importante di questo, cioè nel 2017 ha avuto il premio Nobel insieme a Rainer Weiss e Kip Thorse per la ricerca sulle onde gravitazionali, per un contributo che è stato, diciamo, determinante in questi risultati, e poi tanti altri premi. È anche membro di una serie di organizzazioni scientifiche internazionali come l'American Academy of Art and Science, la National Academy of Science, il National Science Board, l'American Physical Society e così via. Cioè siamo in presenza di uno dei grandi esponenti della fisica internazionale. Allora sono molto lieto di dare la parola al professor Barish.
So let me apologize at the beginning that the lecture's in English. Sorry. I'm going to tell you the story today of the discovery of gravitational waves, historically. So we'll start with the fact that we're here for a special day to celebrate gravitational waves. And you saw a lot about the technology. That'll complement what I'll do because I'm not going to be very technical in describing the instruments today. I'm going to give you more of a historical view of how we managed to detect gravitational waves. So first, congratulations to the university at Sapienza for the new Amaldi Research Center. Eduardo Amaldi was important in many, many ways to science, to peace, to physics in Europe after World War II, to the development of CERN. And he had a particular passion, which he developed here, for developing detectors that would eventually detect gravitational waves. So it's very appropriate, and I applaud the naming of the new research center here after Eduardo Amaldi. The history here started a long time ago with the kind of detector which I won't describe very much today, but the first type of detector that was used to try to detect gravitational waves was called resonant bars. And that began, as I'll tell you historically, in the US by a physicist named Joe Weber, and developed through many years until about the year 2000, when we developed another technique, interferometry, which you just saw, which eventually could be more sensitive. I'll describe kind of why it became more sensitive as I go along. But this detector technique got better and better. This is a picture of the detectors developed here by making them cryogenic, low noise, and running at low temperature. Then the group here worked on the big European detector near Pisa, Virgo detector. Then we worked together with the American detector called LIGO, and we call our collaboration of collaborations. They're two separate collaborations. The LIGO-Virgo collaboration, and I'll show you what we can do together near the very end of the lecture and how that works. And the group here is very actively involved in designing possible next-generation gravitational wave detectors. And you'll see in the lecture that this is just the beginning of a new field, and that just as in other fields, new instruments that will be more sensitive will be developed in the future. And an example of that is the European design of a possible future detector that can pursue the science, which I'll hit at near the end of my lecture. So my story begins 1.3 billion years ago. And we're going to follow this historically. So 1.3 billion years ago, here on Earth, we were just evolving from single cell to multi-cell life. So that's when the story begins. At that time, there were two black holes in the distant universe that, as I'll describe, merged together and formed the signal that took 1.3 billion years to travel from the distant universe to us and was detected September 14th, 2015, which I'll show you. First, let me remind you or tell you what is a black hole. Everybody reads about black holes, and it's a mathematical concept. I'll describe it more physically so that you can understand more or less what a black hole is. In words, a black hole is a region of space where the gravitational field is so strong that nothing can escape, even light. So it's a region truly black in the sense that nothing can escape out of it. And there's a mathematical condition which will give you a black hole. We believe the black holes that I'll describe came, we think, but we don't prove it, that they came originally from the death of a star, or death of two stars. What happens in the star is it burns by a nuclear fusion process its fuel, light elements first. As it burns the fuel, that keeps us warm, gives us light, gives us starlight, gives us warmth from the sun. And as it goes through its life, it burns up the light elements first, and heavier, until eventually it gets to somewhere like iron, and the nuclear fusion process can't go any further. The burning, which gave an outward force on the star, is then diminished. Gravity wins. Gravity causes then the star to collapse, and that makes a black hole if the star is big enough. Our sun will not make a black hole because it's too small. We think that in order to make a black hole, a star has to be about 3 times the mass of our sun or more. So black hole stars that are less than that don't make black holes. They make other particles, other objects. I'll talk about that a little bit later. But at first, when we talk about the discovery, we're talking about black holes that we believe originated from the collapse of heavy stars and that are captured like this, moved around the Earth, 2 of them around each other, and caused the signal, which I'll describe, that we detected. So that's, for reference, what a black hole is. When I show you the signal, we should get the size right. And what I'm showing you in this picture is basically a picture of this part of Italy, and with Rome down here and Florence near the top. And the picture of what I'm going to show you can be superposed on this. And notice the bottom one is near Rome, the top one about at Florence. And that's about the place where we can detect them. But notice 2 things about this picture. First, the black marks aren't very big on this scale, yet each one weighs 10 million times the mass of the sun, mass of the Earth. So it's 10 million times the mass of the Earth concentrated in regions the size of those black dots. And that's what makes such a strong gravitational field. They're separated from each other by only the distance from Rome to Florence, and they're going around each other, as I indicate, by roughly half the speed of light. So this picture is almost unfathomable for us to comprehend. 2 objects, each 10 million times the mass, roughly, the mass of our Earth, only taking up a size of each about the size of Rome, going around each other at about half the speed of light. That's the point at which it enters our detectable instrument. So that's the beginning of the story. This is now a recreated picture of what happens to those 2 objects once they enter our detector. They're going around each other, shown against the universe and galaxies and stars near it. As they go around, they radiate away energy, which we call gravitational waves, which I'll show you. As they lose energy, they spiral in toward each other and eventually make one object and settle down. That's the phenomenon. We detect, this is going on for millions of years, these 2 objects around each other. We detect only the last 2/10 of 1 second when they're merging together in the picture that I drew. That picture was not an animation. It was a reconstruction of the fit to our data using Einstein's general theory of relativity. So that was what we used to draw the picture that I showed you. So that's what happened. And as that happened, as I said, some of the energy radiated away. This radiation, as we'll describe, is in the form of gravitational waves. As it went through the universe, which took 1.3 billion years, it distorts space and time. I'll describe that a little bit later. And when it comes to the Earth, I exaggerated this picture somewhat. It distorts the shape of whatever the space is, which I show in an exaggerated way here as it goes through the Earth. We can't possibly detect the effect on the Earth. It's much, much smaller than we can detect. So instead, we build an instrument, which I'll describe, which can very sensitively see this distortion of space-time as the gravitational wave passes through the Earth. So that's the story in short. I'll give you some details in a minute. As it came to the Earth, the picture that I showed you at the beginning, it entered the southern hemisphere on September 14th, 2015, the first detection of gravitational waves that I'll describe. We know that it came through the Earth in this little banana-shaped area in the southern hemisphere. We know that from the times and shape of the signals that arrived in 2 LIGO detectors that I'll describe that are situated in the US. Those 2 detectors detected it in series some time apart. First, in 20 milliseconds after it came through the southern hemisphere, the gravitational wave came up through the Earth and made this signal, which was detected in an apparatus in the state of Louisiana. And then 7 milliseconds later, almost an identical signal was detected in Hanford, Washington. This is the picture and the discovery of gravitational waves. The picture that I'm showing is data that has not been through big computers and data analysis. It's actually the signal that is seen immediately as the gravitational wave is detected going through an interferometer, like was described earlier, and gives the signal. What's seen is a signal that is going up and down and gets taller and narrower as it moves to the right, making what we call euphorically a chirp signal. That is a signal that goes whoop. It gets higher in frequency and louder as it progresses, a little bit like the sound I just made. This signal, it turns out, fits almost identically in this qualitative signal to the theory of general relativity of Einstein. I've drawn the line through the data that's the fit to general relativity, and you can probably barely see the line. This is without the line and with the line. And so that made us understand immediately that at least what we saw had a good chance of being what we were looking for, which is gravitational waves that at least qualitatively look like you'd expect from Einstein's theory of general relativity. And this is data that hasn't been through enormous computers, fitting, and so forth and so on, but rather just taking what was observed early one morning in these 2 laboratories and putting the fit to general relativity on top of it. That's the discovery. I might comment that this picture here is the picture that then went around the world and was in newspapers. And I was walking down Madison Avenue in New York one day. Madison Avenue is the fancy street, like Via Condotti, where the big fancy stores are. And I saw in a window this picture on a dress. And so I knocked on the door, but the store was so fancy that you can't just go in, it's locked. And you have to lock and push doorbells and know that you belong in the store. I went in and asked where they got this from, and they said there was a designer that happened to be in Los Angeles, where I live. And so I went to the designer when I got home to California, and she made us ties with this on it, which we wore at the Nobel ceremony. So anyway, that's the raw data. Everything I say beyond that is just kind of how we understand it and what we did with the data and what's happened since. So my story now will go back to the human story a little bit, and that is Albert Einstein. We all learned gravity first when we were school kids from Newton. Newton in the 1600s developed the theory, his unified theory of gravity. And that was maybe the most successful physics theory of all time. It described everything about gravity from the 1670s until Einstein came in 2000 or so, in 1900, I'm sorry. And so we had, it successfully described all the motion of the planets, the orbits of the tides in the ocean, anything that, the dropping of the apple, anything that basically described gravity in nature was described by Newton's theory, and we all learned that as school kids. So when you went to school as a school kid, your teacher told you that the apple dropped because the earth pulled on the apple and so it dropped to the earth. The teacher also told you probably that if you jumped up, the earth pulled you down. And I don't know how many of you, but I know I did not, at the age of 7 or 10 or whatever it is when I heard the story, ask the teacher the obvious question, why the earth pulled me down. That was not answered by Newton. In fact, for many years after that, they tried to explain why the earth pulls you down, as Newton described in his famous formula, by using electromagnetism as a method. But it wasn't described by Newton. So we knew that there was one, and Newton knew, there was one problem with Newton's theory. He doesn't really describe why. He just had a nice formula that was the attraction of two masses is the product of the two masses divided by the square of how far apart they are, and with a constant that he didn't know what it was, which described the strength. And that was the famous formula that was used for their ever after. That formula was totally successful, as I said, until one observation was seen in the 1800s, and that's shown here. And that is that a famous celestial a mathematician, actually, Leverrier, in the 1800s had discovered the planet Neptune. And he had discovered the planet Neptune by noticing that Uranus in its orbit around the sun didn't quite follow Newton's theory. And that was the first time anybody saw a possible violation from Newton's theory, is that Uranus was not following the right motion. He then took that information and felt, I believe, that maybe that was due to the fact that there was a missing planet that wasn't taken into account in Uranus's motion around the sun. And he carried through the mathematics, and he basically saw where a planet had to be and what its motion was, and he named it Neptune. And he sent that message to an astronomer from Paris, where he was, to Berlin, gave 5 days for the letter to get to Berlin, and at that point told the astronomer where to look up in the sky, and the planet Neptune was discovered. So he was very famous. This is maybe 1825. About 1850, he found another problem, and that was the problem of Mercury, which is our planet nearest the sun, and its orbit around the sun. So being famous at that point, having used a technique once and made a discovery, he assumed, or he theorized, that maybe there's also a problem in Mercury's case, which has to do with possibly a body or bodies between Mercury, the planet closest to the sun, and the sun itself. He called it Vulcan. So he basically assumed or thought there's something in between Mercury and the sun. Various experiments were done in the late 1800s looking for a Vulcan, just as the planet Neptune had been done. There were even some discoveries made, but they proved to be false. So everything I've told you then brings us up to Einstein's time. This is the only discrepancy that existed. It could have been due to the fact that there was planets or some masses between Mercury and the sun, but none had been seen. So it was a puzzle, but unlikely to be what motivated Einstein to spend 10 years after he had introduced the theory of special relativity in 1905 to develop the theory of general relativity in 1915. But his theory of general relativity, which is the theory of gravity that we use today, and that I showed you the fit through our data, was developed and brought out by Einstein in 1915, and it did solve two problems that Newton's theory had. One is it does explain why the apple falls to the earth, or why the planets are attracted, and it has to do with these words that we've all heard, that's curvature of space and time. that the structure of space and time being curved creates a pattern where objects near each other can be attracted to each other. The second problem that Einstein's new theory of gravity solved is a problem that we call instantaneous action at a distance. So in the case of Newton's theory, at a distance when the stars collide, you'd see the signal immediately. Or when the apple falls, you see it immediately. That can't be true for objects at a real distance. So for example, if the sun were to burn out right now, we wouldn't know it for 7 seconds, the time it takes light and heat to come from the sun to us. But the gravitational wave signal must also take, signal from gravity must also take that long. So Newton's theory didn't have that mechanism. Einstein's does, in that Einstein's theory of gravity, all the objects, gravitational waves or signals from gravity or from electricity and magnetism, travel at one maximum velocity. We call it the velocity of light. So those two problems were solved by Einstein's theory of gravity. This problem, which is Mercury around the sun, had only a small discrepancy. I write it here, which is about 10%. If you use Newton's theory of gravity and calculate how long the orbit takes to go around, how far apart it comes, it goes around and it moves a little bit when it goes back to its next position because of the location of all the planets and so forth, the masses around the sun. You can calculate from knowing them all where it's going to come back, and it moves by 575 arc seconds per century, and the actual calculation by Newton was only 10% less than that. Einstein, when he introduced general relativity, which is a little bit more complicated formula, which you can see here, his theory of gravity actually got the right answer. So the first issue when a new theory is developed is that the theory should explain problems that you had before and fix them, but that's probably not enough to make a new theory acceptable or adopted, especially after 200 and some years of Newton's theory. So it should predict new physics beyond just fixing a problem that might have existed. In this case, the new physics that it immediately predicted, that Einstein immediately predicted, was the problem of bending of light. And you'll notice in the picture on the left that I show here, that I have a picture of the Earth, of the sun, and a coordinate system below. The coordinate system below you might think of as a trampoline, which is just a two-dimensional object. The presence of each of the other objects distort that, and what you see in this picture here is that this grid got distorted by the presence of the sun, and there's a little dimple out here because of the presence of the Earth. Each point on here is actually, I can't show it here, is distorted in 3 space dimensions, but also in time, which I can't show in this picture, but all of those get distorted in the presence of a massive object. So in the picture here, it's obvious that there's a downhill slope between the Earth and the sun, and so it wants to be attracted to the sun. The fact that it's moving at velocity around, by centripetal force, it stays in an orbit around the sun. So basically, Einstein's theory, although much more complicated to look at than the simple formula that I gave you before, much more complicated to deal with because it's 4-dimensional, space and time being unified together, solve these 2 physical problems, and is our present theory of gravity. And one of the things that we want to test as much as we can as we experimentally investigate gravitational waves is the validity of this theory versus maybe improvements to it are variants of the theory of general relativity. And we're just beginning to be able to do that, and we'll be able to do much better in the future. So testing this theory of gravity in detail is really the future that we have. So that's the theory of general relativity or gravity that we have today, and it's an active and important area of research in physics. This was presented first by Einstein in 1915. In 1916, the next year, Einstein wrote a paper where he presented the idea that there were gravitational waves. So what do we mean by that? This is less than a year after the first paper. So in 1916, he wrote this paper here, which proposed that there are gravitational waves. It's not a very good paper, but it proposes gravitational waves based on similarities between the equations that he could write in a certain form from general relativity and equations of electricity and magnetism. And he didn't derive gravitational waves from fundamental principles, but made a leap from the fact that it looked like to him the same kind of equations that exist in electricity and magnetism, that there must be gravitational waves. In electricity and magnetism, we have electricity, a lot of forms of electricity, including the lights above our heads. We have magnetism and magnets, which we all know, and we have all forms of electromagnetic waves, light waves, radio waves, microwaves, and so forth. So seeing that the equations have a similar form, he projected that there must be gravitational waves. This paper, as I say, wasn't really either very good because it wasn't really from a fundamental derivation. And it also had mistakes in it. It has a mistake of a factor of 2, which he fixed the next year in 1918. So he wrote a second paper in 1918 where he basically fixed the factor of 2 error, and more importantly for us, people like myself as experimentalists, he dealt with what the source would be of gravitational waves. And we all know that electromagnetic waves come from taking 2 charges and oscillating themselves like this. And that was done first by a physicist named Hertz in the 1880s, where he took 2 charges, moved them up and down in one room, went in the next room and detected the fact that they had emitted electromagnetic waves, moved his detector forward and backward toward the source, and saw that it was wave-like, and that was the discovery of electromagnetic waves. That was Hertz in the 1880s. So you can ask if you can do the same thing for gravitational waves somehow. But first, the source is not this, but what we call a quadrupole, which is 4 different things going around. And that was shown here. Anyway, before I get to that form of it itself, after 1918, Einstein didn't revisit or talk further about gravitational waves until the 1930s. By the 1930s, Einstein had immigrated from Berlin to Princeton University in the US, and in the 1930s, he wrote a paper where he questioned whether gravitational waves would even existed. So this was because he was dealing with how to develop it from first principles out of the theory, and found what we call infinities in his formulation. He thought that maybe those infinities were then causing him to believe that there were gravitational waves when maybe they didn't exist. He turned this in to be published. It's a long story. In the end, he basically ended up republishing it, not in the original journal, in a form that basically was more closer to a derivation of gravitational waves. But what I'm pointing out is that even in people close to general relativity, it wasn't clear 20 years later that there were gravitational waves. And in fact, it wasn't clear to the broader theoretical community as late as the 1950s. And most people attribute the point at which most theorists believe that gravitational waves exist to a meeting that was held in Chapel Hill, North Carolina in 1957. That meeting was chaired by 2 prominent physicists, Cecil and Bryce DeWitt, and had 44 of the most involved theoretical physicists in the world, 1 experimentalist that I'll describe, at a meeting where they described where they discussed whether gravitational waves exist. So it was pulled together to do that. That's the 1950s. And at that meeting, the highlights, I think, from my point of view, was the beginning talk by a general relativist named Pirani, British, who basically came as much more elegantly to a derivation from first principles of gravitational waves out of general relativity. That hadn't been done, at least very much to convince people before, so that was a nice proof. And then at the same meeting was Dick Feynman, who was my colleague at Caltech, and he, as he often does, tried to ask the question more physically. And he presented at that meeting what he called the sticky bead argument. And the argument was simply the following, that if gravitational waves exist, somehow they have to be capable of transferring energy. Otherwise, they're just an artifact. So how could they transfer energy? This is his picture from that conference, which he called the sticky bead argument. And the argument was just the following, that if you have a rod like this and you put a couple rings around it, and then a gravitational wave comes through, it changes space and time, as I said, expands and contracts the bar itself. That puts some friction on the beads, and they move back and forth. So that's basically happening by friction, and friction is then a transfer of energy, and that's a kind of physical argument, at least given in a few sentences by me, of what he was talking about. So both physical argument and mathematical argument were given in 1957. This all could be construed as a kind of excuse by me and my colleagues in experimental physics that it didn't really take us 100 years from Einstein's proposal that there's gravitational waves until detection. He proposed it, remember, in 1916. We announced it in 2016. The first 40 or 50 years was used up by theorists and not knowing whether there really were gravitational waves. But at this point is probably the turning point at which the problem became experimental. So it took another 60 years after that before we could tell gravitational waves. The first attempt was to do something that was very much like the sticky bead argument of Feynman. That was done by a physicist at Maryland at that point, Joe Weber, who had been at Princeton before and was at the meeting in Chapel Hill, North Carolina, which must have been the genesis of the beginning of the idea that you basically could build something that looks like the sticky beads. What he did is take a big bar of aluminum and around it put very sensitive detectors that if the gravitational wave goes through and expands and contracts the bar a little bit, like I showed in the picture of the Earth, that these very sensitive detectors would pick up the signal and it would be detected. So this was the first experimental attempt to measure gravitational waves. I showed a little earlier a picture of the Explorer. There's also the Nautilus detector that were developed here, and those are much more sophisticated versions of the bars done cryogenically so that they were much quieter, but not able to detect gravitational waves. The technique that I'll describe next is able to detect gravitational waves, not so much because it's so much better, but by brute force can be made the right dimensions. That is, this is roughly 1 or 2 meters long, and we're capable, as you'll see, of making detectors that are kilometers long, and that makes the problem much easier. So this is the first gravitational wave detector made by Joe Weber, and versions many years later, 4 many years that were developed, first because Eduardo Amaldi was interested in developing these detectors, and then later by colleagues after that, and these are 2 detectors that come from the research that was done here. And the key was it was made cryogenic to reduce the noise that limits the system. The size inside is similar, meter or 2 meter long detectors. And by the year 2000, when we started in gravitational waves in interferometers, which is the other technique, a whole network of these existed in the world, and we're looking for gravitational waves. Also, they had succeeded not only in making them much quieter by making them cold, but the natural physical response and why a bar is sensitive is if you walk up and you hit a bar, kind of like you heard here, it'll ring at some resonant frequency, but that's very narrow. And very good work was done to make a broader range signal here, which is shown up here, which got as broad as 100 hertz. The technique that I'll talk about that we used to detect it had two advantages. One is we could make it kilometer length instead of meter length, and the other is it can cover thousands of hertz bandwidth rather than just 100 hertz. And those are both very big advantages and why we now use interferometers. Maybe there's better techniques that'll be used in the future, but right now that's the best technique we have for doing gravitational waves. So now let me try to give you a sense of how well we have to do what we do to measure gravitational waves. So first, what I do here is to show you how hard the problem is. First, as I said, they're basically distortions of space-time, ripples in space-time itself. I might point out that those ripples are truly in space-time itself. If that object that I showed you at the beginning transmits a gravitational wave signal to the Earth, it's not like photons in electromagnetism, where you have a propagator called photons. But here, it's actually a distortion of space and time itself. There is no equivalent carrier necessarily. So there are ripples in space-time itself, much more like going to a pond of water and throwing a stone in, and there's the ripples that go out, but there's nothing in those ripples, so the water itself. So basically, that's the phenomenon. It goes through space at the speed of light, which is the one speed in the problem. The amplitude of the wave, this little h is the term from general relativity, but it's the amplitude of the wave that we have to measure, has a size of 10 to the minus 21. It's the number that matters. When I showed the signal that's on the dress or the tie that I showed, if you looked at the scale, it was 10 to the minus 21. So the scale that we have to be able to measure is something like 10 to the minus 21. So let's see how big of an effect that makes. And I try to show that here. That little difference, 10 to the minus 21, is proportional to how much something of some length will change. 1 part in 10 to the 21, small number. And that's delta L. The reason for that, why it's so small, is also pretty easy to explain. Gravitational waves, if nature were described differently, they could be big. But we all know something about materials, and materials are described by things like Young's modulus and different ways to describe it. But you know, some materials are flexible, some of them are very stiff. Space itself is incredibly stiff, is the simple reason why the distortions are so small. So if I wouldn't want to do it by somebody who kind of thinks of it as materials, then space itself is just hard to distort. So let's see how hard. If we want to look at a change of length, then it's proportional to this little h that we measured times the length. This is 10 to the minus 21. So the effect of how much this circle, if I have a circle of just free masses, they're free to be moved if a gravitational wave comes through, this little difference here is only going to be 10 to the minus 21 meters. And that's basically what has to be measured in these bars. We get to make the problem somewhat simpler because we make, by a different technique, detectors that are 1,000 times longer, and so this number becomes 10 to the minus 18 meters. Still a pretty small number, but 10 to the minus 18 meters instead of 10 to the minus 21. That had to be done in the bars. So how small is 10 to the minus 18 meters? Let me remind you, just so you know how hard this is. First, we all know what a meter is. It's that long, and we're pretty good at measuring it. So a meter stick, that's something we can all relate to. 10,000 times smaller than that is the human hair. I don't have very many left, but that's basically 100 microns in size, and we all can see a human hair. The next size smaller is the wavelength of light. This laser beam that I have here is about a micron, or 100 times smaller than human hair, the wavelength of the light in this laser beam. So we can all go kind of that far and relate to it. If we go to atomic distances, then an atomic diameter is about 10 to the minus 10 meters, or something like 10,000 times smaller than the wavelength of light. So that's getting to be pretty small. And then if we go to CERN, or somewhere where we look at nuclear effects, then the proton itself is 10 to the minus 15 meters, or 100,000 times smaller than the atomic diameter. And to study that, we have huge accelerators, like the CERN accelerator. And for us, we actually have to measure something that's 1,000 times smaller than the proton. So that's the challenge. And the reason it took still more like 60 years to develop a technique that could measure something so small. It turns out in physics that measuring an absolute size is often very hard. And in fact, we have big institutions to do that. So in the United States, we have a big institution called the National Bureau of Standards. And that whole big institution, which has thousands and thousands of people, are responsible for making sure that the standard for what a kilogram weighs, what a meter is, and so forth, are standardized. And it's very difficult. There's another one in Paris, and this is always a big area of fundamental physics to keep the standards that we use to measure things, the weight of a kilogram, the size of a meter, and so forth, standardized around the world. As an experimental physicist, it's often easier and much more precise to measure small differences in two things that are normally the same. And that's what interferometry does. And in interferometry, we have a natural technique to measure a small difference, and we can do that much, much better. So measuring the absolute size of 10 to the minus 18 meters would be impossible. But the fact is, measuring the difference is possible by measuring the effect. So what I show in this movie here is dividing a beam of light in two directions. It comes from a laser, it goes in two directions. That's the wavelength of the light. You split half of it in one direction, half of it in the other. If the length down to a reflecting mirror is the same, they'll come back at exactly the same time, and they'll cancel each other, which they do in this picture here, and no signal is seen here. That's interferometry, and we start with a basically null condition, no signal. But if we change the lengths a little bit, these won't line up, and they can add and they give a signal here. And that's what you saw in that very first slide, that the length of the two arms became not the same as each other, and we saw, as a result, a little signal. And that you can do very precisely if you're careful, because normally there would be no signal, and we look for a signal where there would be no signal, rather than looking for deviations in a meter stick or something, which is much harder experimentally. So we use this technique of measuring the difference. The challenge is shown here. The challenge that took 60 years, I reduced to two numbers. And for today, that's good enough. The two numbers describe two problems. One is, how do we do this interferometry that I just showed you well enough that we can see the difference of 10 to the minus 21? To do that, we have to basically do this interferometry. We saw a wavelength of light going like this, to 1 part in 10 to the 12th, that's a small number, the wavelength of that light. Some of you have used an interferometer, like you saw at the beginning of the lecture, and often you see some what we call fringes from the interferometer arms being slightly different from each other. And in a college physics lab, you probably can see those differences to 1 part in 10 or 1 part in 100. People who do interferometry really well might be able to do it to 1 part in 10 to a million even, and that's phenomenal. We have to do it to 1 part in 10 to the 12th. And so these interferometers, which I'm not going to describe today, are incredibly sophisticated in terms of almost everything you can do to make the interferometry incredibly sensitive. So one of the parts of the problem is to develop the interferometry so that it's incredibly sensitive. And that's been done in the US, been done here in Italy also in the Virgo detector, somewhat differently. There's different ways of solving the same problem technically and experimentally. But in both cases, the problem of trying to do this interferometry itself much more accurately than we do interferometry in normal usage, whether it's in a physics lab or as an instrument, it's never done to 1 part in 10 to the 12th. That's one part of the problem. The second part of the problem is that the Earth vibrates like crazy. Even though it seems steady when we're standing on it, it's actually moving a lot. And so as an instrument, we just happen to be here on Earth. We don't want to have anything to do with the vibrations of the Earth itself. So we have to separate the object, the instrument, from the Earth itself. We have to get rid of any shaking of the Earth and suspend it somehow so that it's just here where we happen to be living to use it as an instrument. And that problem is also to reduce the shaking of the Earth by 1 part in 10 to the 12th. So I've oversimplified simply, but I wanted to just give you 2 problems that had to be solved to measure gravitational, to be sensitive enough to measure gravitational waves. One of them was to do the interferometry that I'm showing in this picture here, much better than it's done by people that use interferometers, and we've done a lot of tricks to do that. And the other is to isolate ourselves from the Earth by 1 part in 10 to the 12th, an astounding number. I'll show you how we do it in the US, which is a somewhat different solution, but equally valid to what's being done here in Italy. This is the detector here in Italy, the Virgo detector, which is in Cascina near Pisa. And I'm not going to talk about it further, they have a very sophisticated way to basically make isolation from the Earth in a very tall tower of isolators to isolate us from the Earth. This is just a graph that shows that. You'll just notice this is many decades, this is frequency, and they reduce it by essentially the same amount that we do. We use a different technique, which I'll describe. In the US, we actually built 2 detectors. Those 2 detectors are in 2 different states, Louisiana and Washington. If you ask me why they're in Louisiana and Washington, because the 2 home institutions are in California and Massachusetts. The answer is politics. We asked the government for money. The government, of course, gave us money, but they favored certain political elements, and so they rotated it. We're in the state of Louisiana and the state of Washington. We had nothing to do with that decision. They look very different from each other. The state of Washington is high desert. Almost nothing grows there. It's very stable, high desert. And the state of Louisiana is basically swamps. It's water and lots of forests. It's in a forest. And the water table is just a centimeter or so below the dirt. So as soon as you dig down, you hit water. You can see that in the picture, because in order to keep ourselves from flooding, we built the instrument up about 6 meters above the level ground. In order to get the dirt to build it up, we made a ball pit next to it, and it immediately filled with water, fish, alligators, and so forth. This is the inside of LIGO. These isolators, as I'll talk about in a minute, are not as tall as in Virgo because we use a different technique. But you notice all the ports. So this is a picture. This picture here is about 3 times the height of a man. And you notice the ports all over the place. We were very careful at the very beginning when we built LIGO, which is the late 1990s, to try to anticipate everything we would ever want to do with LIGO to make it better to eventually detect gravitational waves. Because building infrastructure is more costly than building technical equipment. So we wanted to make sure that we built the infrastructure once and could build all the technical equipment. So we have A lot of what's evident here is the many, many ports, ways to get in, places you can put instruments, and so forth and so on, of which we only use a fraction of those. But it enabled us to go to what I'm going to show you, the improvements that eventually made us sensitive enough to detect gravitational waves. So this is our solution, and for those of you that are asleep, this is the time to wake up, because this is the one slide that is the improvement that we made that enabled us to detect gravitational waves. So what we did originally, in this picture here, this is the isolation from the Earth. Our way of isolating from the Earth initially was to do what's done in your car, in your automobiles, in your cars. That is, make shock absorbers like you have in your cars. They're just little springs, but they're very, very sophisticated springs. And we made 4 layers of them, and that was what provided our isolation from the Earth. Secondly, we suspend the mass. The mass is on a pendulum. And if I hold a pendulum like this and move it on the top, it doesn't do very much to the mass itself. If I take a mass and it's down here and you do this, it doesn't do very much down there. So a combination of suspending the mass and making all the shock absorbers, and for us, gave us at the frequencies that we needed to detect these gravitational waves, an isolation of 10 to the 10th, which you'll remember we needed 10 to the 12th. So the car shock absorbers, which we had 4 layers, we made them as sophisticated as we could, wasn't good enough to solve the problem. We anticipated this. In the years starting at about 1999, we started developing what we called active isolation. And that is, in addition to the shock absorbers, to measure with seismometers the shaking of the Earth and the direction of the shaking, and then compensate for it by pushing back so that the masses themselves, or mirrors, would stay stable. And it took us a decade to develop that technology, but that was installed newly into the detectors at the time that we made the detection, and it's the simple reason that we were able to make the detection. So think of it as what you do when you get on an airplane. If you get on an airplane, many of you have put on these earphones that make the annoying roar of the engines go away. That's done by detecting the ambient noise from the engines and then canceling it actively. So we do the same thing. We just borrow car shock absorbers, then borrow the idea of the earphones that you wear in an airplane. The difference is, in our case, it's much harder because we have to not just hear the roar of the engine and cancel it, but we have to measure the direction and the magnitude of the noise and correct for it. So that required a whole array of seismometers, measuring the direction and pushing back. That took us a long time to develop. But the simple idea is very much like the earphones in an airplane. So this is the improvement we got. This is all LIGO now. This here, the top picture, this is frequency. We measure the audio band. We have nothing to do with audio. It's nothing to do with sound. But where the Earth is quietest is in the audio band. Our ears know that by evolution. So they've picked where the Earth is quietest so we can communicate with each other. But for us, it's the same. We have nothing to do with audio, but it's where the Earth is quietest. So from something like the Earth starts at tens of hertz to thousands of hertz is where we can work. So the same frequencies as you hear each other. The scale on this side is the level of that little h that I showed. Notice the numbers, 10 to the minus 21, 10 to the minus 22, 10 to the minus 23. Very similar to the numbers that I said we needed to detect. And this is going from 10 hertz, 100, 1,000, 10,000 hertz. So that's where we are. After 20 years on LIGO, from 1994 to 2014, the best sensitivity we ever got is shown here. Above this is where we can detect something. This is where it's limited. The little vertical lines are mostly due to disresonances in the system. If I build any experimental system it'll have various resonances in it. Resonances that come from the fact that you use, in our case, 60 hertz, here 50 hertz, and there's multiples of that electronically. Any stand I have has resonant frequencies that it likes to shake at. That makes these vertical lines, most of which we can just notch out of the data, and it's 1%, so just ignore that. And this is the shape that we had before we added the improvements that included a more high-power laser and so forth, but the one I'm concentrating on today is the active seismic isolation. So at high frequencies, you notice we went from here to here, we improved about a factor of 3. But at low frequencies, here I picked 40 hertz, it improved a factor of 100. And that was the factor that made us go from 10 to the 10 to 10 to the 12. You remember we had to isolate ourselves from the Earth by 1 part in 10 to the 12th. So this is our factor of 100. Also, one of the questions I often get asked is how did we somehow manage to detect gravitational waves in 1 week after we turned on this new detector when we hadn't seen gravitational waves in 10 years before that. This improvement of a factor of 100 in terms of rate has to be cubed, because what we measure, this, which is on this side, is directly proportional to how far we look out in the universe. So if we make ourselves 100 times more sensitive, we look 100 times further out, that's 1,000,000 times more volume, stars, galaxies, and so forth, and therefore the rate of gravitational waves goes up by 1,000,000, not 100. And so in a week, we're much more sensitive than we were in years of running with the less sensitive detector. But it's this improvement due to active seismic isolation in LIGO that brought us to the level where we could make detections, and then we saw these detections. So to remind you, this size here is 10 to the minus 21, you'll notice. So the signal got up to 10 to the minus 21. It's noisy, so it isn't because we're down at the level where we can barely measure it, but it's oscillating up and down, getting narrower and coming together. And this is the one in the second detector, the one in Hanford, Washington, and one in Livingston, Louisiana, 7 milliseconds apart in when they came. Okay, we fit that then to Einstein's equation. Einstein's equations, which give a picture like this, very much like the picture you saw in the data that I showed. In fact, it fits it extremely well. So in Einstein's picture here, what's happening is that out here, in this region here, 2 objects are going around each other. They're still fairly far apart. When we move in here, they're getting closer together. In this region, where it gets very sharp and big, they're merging together. And then finally, there's some sort of a settling down that we call ring down that's at the very end. And so that's the characteristic shape that we expect for this kind of gravitational wave. That is the coming together of 2 objects that are in spiral due to the radiation of gravitational waves away. Look at the bottom graph because it tells the rest of the story. First part is how far apart are these 2 objects. This is in units that are about 50 kilometers each. So they start about 50, 100 or so, 200 kilometers apart, and as they come together, they're very close, about 50 kilometers or less together, and that was the distance that I showed, more or less, between Florence and Rome. The speed is also shown here from Einstein's equations, and when they first enters our detection, it's more than a third, or about a third of the speed of light, and by the time they come together, it's over half, or something like 0.6 times the speed of light. So these 2 objects are very much like this incredible picture that I showed. They're very small, very compact, very heavy, and going around each other at relativistic speeds. Okay, that's the first detection, and then we detected, which shows here, we saw the last 0.2 of a second, and I showed that. 4 months later, 3 months later, in December of the same year, we saw this detection here. This one we were never sure of, came in between, but we couldn't have the confidence that it was right, although it probably was, it wasn't as significant. But we saw this one on Boxing Day, December 26th, the same year. That gave us complete confidence because these are so different from each other. The reason this one looks so different from this is they're not 30 solar mass objects, but they're much lighter. If they're lighter, they go to higher frequency, and we detect them from many, many more cycles, but they're not quite as big. And so this was our second event, seen in December of the same year, and these are subsequent events that we saw after that. Notice the time of even this long one was up to almost 2 seconds, but it's still pretty short. The first one was 0.2 of a second, then 2 seconds. Okay. Now a little more of the story. So that was the detection. We did that in 2015, both of those detections and the further ones after that. Well, last year we were joined by the Virgo detector in Cascina, which a strong group here in Rome work on. And we made a detection last August, this means August 14th, 2017, of a black hole merger, just like the other ones that I showed you, but now with 3 detectors instead of 2. These are the 2 LIGO detectors, one in Hanford, one in Livingston. The stronger signal was in Livingston because it was working better at that time. And one here, which wasn't quite as strong because they're not quite as sensitive yet in Virgo, but they're catching up, and this is the signal seen in the Virgo detector. So all of a sudden, we now have 3 detectors in the world detecting gravitational waves rather than 2. This is a big step because you'll remember in the very first pictures, I showed big regions like this of how well we knew where the signal was coming from. Once we were able to use both Virgo and LIGO together, we got a signal that was this well located instead of these big bands. Why does that matter? It matters because we want to see, not for black holes, it doesn't matter because they don't see it, but for any other signal, we want to see if any sort of telescope, whether it's infrared, ultraviolet, visible, see signals that we can help understand what the objects are. Black holes, since they don't give anything else, are just owned by us. But for other objects, it might matter. So this proved for us that we get a huge gain in being able to point, and that will enable us to tell telescopes where to look if we see something that wasn't just black holes. And that was with the adding of the Virgo detector. And then 3 days later, we got this signal. And this took this long. This is all a gravitational wave signal you're listening to. It went for tens of seconds instead of a fraction of a second. And when it gets near 0, which is here, you'll hear this characteristic little chirp. I'll be quiet, you can barely hear it, but you should be able to hear it as I get near the 0. This is the signal for gravitational waves. You can see it along here. Did you hear it? Somebody, maybe. Anyway, there were little chirps went whoop as you came near the end. So that signal turns out to be very different. Why did it stay in the detector so long? And what did it mean? It was not black holes. Instead, this signal, which I've shown here, you could see it before, but I've shown here is, this is frequency, this is time. It gets to higher, narrower and narrower, higher frequency. We saw it here in time. This is the 2 LIGO detectors and the Virgo detector. And then we knew where it was in the sky, which is shown here. The combination of our 3 detectors pointing to this smaller region in the sky. And unbelievingly for us at the time, since it's the first one we ever looked at like this, 2 seconds later, it was also observed by a satellite looking at high-energy gamma rays in exactly the same direction. So they saw it in this picture here. And the overlap between the 2 meant for the first time we were detecting an object that was also seen by regular astronomy, which is pretty fantastic. The object, because it took so long, was not black holes. It was what we call neutron stars, which are the product, or can be the product also of the end of life of a star, but are much lighter and they're nuclear material. They weren't strong enough gravity to make a black hole, but it's a very compressed amount of nuclear material. if it's nuclear material, it can make nuclear reactions, give gamma rays, give light, and so forth. So this, once we saw this, we announced immediately to telescopes and astronomers around the world that we saw this signal. And basically, there's something like 4,000 astronomical instruments, major instruments in the world, and about half of them pointed in that direction in the sky as quickly as they got the signal. That involved ourselves in gravitational waves, visible and infrared light, radio waves, X-rays, gamma rays, even neutrinos. So everybody looked at that direction in the sky, and the picture that came out is shown in this graph, which I can't take the time to go through, but this is all the different wavelengths in light, all the way to the radio, starting with high energy gamma rays, and the kind of signals they saw. That has all been reconstructed in what happens when these two objects come together in terms of the nuclear physics and coming together. And it's a phenomenon which is called a kilonova. We know what a supernova is, and a kilonova is, a supernova comes from the collapse of a star. A kilonova is this in-spiraling, at least named that by a phenomenology of a theory group at Columbia University. So they tagged this name, and everything fits that picture. One outcome of it, I can't go through all the beautiful physics done here, but I'll show you one outcome for this audience. And that is that we've always had a problem for a long time in physics describing in the Earth how the Earth came together in its history. And if we go down in mines, we find very heavy elements like gold, platinum, and so forth. Where did they come from when the Earth was formed? Physicists always find some answer, but it's not necessarily the right answer. So the problem is that mostly the universe is made out of hydrogen and helium. And then we have stars that collapse, but I described to you that the nuclear fusion process only goes up to about iron. So where did the heavier elements come from? When we read about new heavy elements in the newspapers, we know how to do it in the laboratory. We basically take some heavy element and we bombard it with lots of neutrons, and we make a heavier one, give it a name, it gets anointed and added to the list, and that's where the heavy elements come from. But that just says they exist. How did they get somehow in the Earth in a mine? And now one explanation of that, which is not definitive because we only have one example, one event that we found so far, is that maybe they came from the merger of these neutron stars that we just detected. After all, in the lab, we use neutrons to make the heavy elements, so the neutron stars are a logical way to do that. People try to analyze whether that's possible from the data we have, and I've just taken one example of that. It's not definitive, where the yellow ones, the yellow parts are the heavy elements, the contributions to the heavy elements that came from past, not the one that we just did, past neutron stars coming together like the one we saw historically, making the heavy elements that then existed to be part of the Earth when the Earth was formed. You'll notice that maybe your favorite heavy elements, like the rings on your finger, platinum and gold, actually might have come from what I talked about a few minutes ago, which is the merger of two neutron stars. Let me just say a couple words about the future, and then I'll end. One thing that we want to do is to be able to point better in the sky all over, independent of where the gravitational wave event is coming from. So we were fortunate when it was detected by Virgo and LIGO, in that it was in a position in the sky where we could tell the direction quite accurately. But there are unfavorable directions in the Earth. We don't cover the southern hemisphere very well, and so forth. And so we expect to have, by 5 years from now or so, 5 detectors of comparable sensitivity working in the Earth. The Virgo detector here in Italy, the 2 LIGO detectors, a detector in Japan, and one in India. That combination will give the difference between today, which is this picture up here, where some of the areas we don't do very well, these are these banana-like shapes where the pointing is, to the one down here, where anything we detect anywhere on the globe, we should be able to tell to good enough accuracy to look at counterparts that exist from astronomical instruments. So this is to say that this science will keep evolving. We're just beginning. Our plan is shown here, where this is more or less the sensitivity as a function of time. We're now here somewhere, and we expect to start soon. The numbers here are how far out we can look in the universe with LIGO, as I've used for an example. So we're going to run again soon, starting probably this coming spring, and be maybe almost a factor of 2 better than we were before. Remember, we cubed that number to see the sensitivity, and we'll keep improving through the decade. So one can look forward to this science getting better and better with the present detectors as we improve them, and then people are already working on how to make further improvements and better detectors. We're not limited by nature. We're limited by our ability to make instruments that are sensitive enough. So we can keep doing better. It took us a long time, but our problem is more making a sensitive enough instrument. This is just a graph to mention a couple things on the right of how we plan to improve the LIGO detectors in the coming years, which involves making bigger test masses, maybe different materials for the mirrors that are better, have less noise, silicon we're talking about. Lowering the temperature of the detector, noise is less if you lower the temperature. It's hard to lower the temperature because it's a technical issue. Making better mirrors that actually match the problem better, and more powerful lasers. So those combinations are basically the improvements that we make. That'll immediately give us the ability to go back, to look further out in the universe, which is going back further in time, going to earlier times, which means more cosmological in the future, improve our signal and noise rates, which means that the cleanliness of the events become much better. That will enable us to test, for example, general relativity and see whether there are variants or differences from Einstein's theory of general relativity that we can detect, and so forth. There's been a lot of work in Europe and plans and aspirations and hopes to start to move forward toward a next generation detector, which will be at least a factor of 10 better than we can do with the present detectors in Italy and in the US. And again, that's been worked on in design level, and we're hoping that this evolves both in terms of the scientific potential, the technical way to do it, how many in the world, what they should look like, and so forth, and understanding the science potential, and then lastly, getting the resources from governments to do it. Lastly, let me just reflect, this is my last slide, that in 1608, Galileo, for the first time, took the fact that people had developed lenses, mainly for glasses, at that time, and made a telescope. And he looked at Jupiter. And looking at Jupiter, he discovered there were 4 moons in Jupiter. It's been 400 years since then. And in 400 years, that was the birth of astronomy beyond just doing it with your eyes, doing it with real instruments. And we've had 400 years of astronomy since then, and what we know about the universe since then using astronomy is phenomenal. It's presumptuous, but I think we're kind of at the same stage for gravitational waves. We've made the equivalent of what was done by Galileo in 1608, that is, look at the first kind of signals that you might see with gravitational waves. We hope that it develops maybe as richly over the next tens and hundreds of years, just like 400 years for modern astronomy, hopefully eventually getting to do problems that astronomy can't even touch, sources that don't give astronomical signals that would be big, some completely new science, going and studying the early universe, where astronomy can't go earlier than 300,000 or 400,000 years after the Big Bang because everything, all the photons get absorbed earlier and so forth. So we think that we've opened the window just a crack on what should be a new science in the coming tens and centuries. Thank you.
Ringraziamo il professor Barry Barish per questa bellissima lezione. Immagino che ci saranno delle domande, quindi ci sono delle persone che...
Barry.
Yeah.
I congratulate for the lecture, and we are living in a very, very exciting moment of our knowledge of the universe. Especially now, thanks to the development not only of this new technology on gravitational wave, we are observing practically every day the birth of a black hole in gamma-ray burst. This allows us to map practically the entire universe, because gamma-ray burst is 10 to the 54 erg, enormous energy, and it will be very interesting since we have now 8 different families of GRB. Some of them, 3 of them, can emit a large amount of gravitational wave. Therefore, it will be very important in the forthcoming years to try to correlate together the observation of GRB, which we are working very much in our group, and the work of the gravitational wave people, which were born here in this department 40 years ago at the same time.
Thank you. Let me just comment that the very last event that I showed, I may not have used the words, I just want to make sure that I do, was a first simultaneous detection of gamma-ray bursts and a signal from gravitational wave detector. And as predicted here, there's much more to come in the future. And
okay, so maybe it's just the student's question, but the gravitational wave can be diffracted by other gravitational wave. So is it any chance that the gravitational wave which we already observed was maybe some interfered gravitationals?
Student questions are the hardest questions. Yes, you're right. Another question I get asked all the time, both at the same time, is whether we have a problem, which I wish we had, of multiple gravitational waves affecting the instrument at the same time. I think those kind of problems that you're talking about are way in the future. When we're barely able to see gravitational waves, we have to see the strongest thing possible, and that's a single gravitational wave coming from for us. In the future, we look forward to when we have confusions that we have to worry about.
Thanks a lot.
So my question is, should the gravitational wave explain more about the weaker force of gravity? I mean, gravity is weaker than the other forces. So could the gravitational wave could be an explanation of this problem?
The question was a recognition. The question had to do with the recognition that gravity is our weakest force. It's kind of not intuitive because all of us from the time we were children experience gravity more than anything else, but it's because we have the whole Earth pulling on us, or the effect of the whole Earth. It's the weakest. This gravitational waves are a product of general relativity and gravity, not an explanation of general relativity or gravity. The strength of the different forces that we have in nature are kind of what we experience. We don't have a theory of why yet. I mean, we talk about grand unification, bringing them together and understanding them, how they deviate at different regions of time, of energy. And so grand unification of all the forces is a goal that physicists have had. We don't have that. But gravitational waves are not an explanation of the difference of the forces. I think it's more a product of gravity itself, a feature, just like electromagnetic waves are a feature of electricity and magnetism.
So regarding the upcoming projects to detect gravitational waves, what about the detector LISA?
Oh, good. So the question had to do with the detector, which in America we call LISA, and she called LISA. It stands for Laser Interferometer Space Antenna. And it is a future project, actually sponsored by the European Space Agency. NASA, which is the American Space Agency, used to be part of it, but it's now a European project. The Americans may join it. It's the future gravitational wave experiment to put in space. And why is that useful or interesting? I spent this whole hour talking about frequencies that our ears respond to. That is the frequency band that we respond to. And if we want to go to, like we do in astronomy, to different wavelengths or different frequencies to understand the science, then we want to do gravitational waves also in different frequencies. And to go to lower frequency, we have to get off the Earth because the Earth shakes too much. And so an experiment in space is ideal for going to the next lower frequency band. There's a very mature design, even tests of the technology that have been done for LISA. It's a project that has been approved by the European Space Agency and will fly, I think. It should. Unfortunately, the time scale is the time scale of space exploration. It's scheduled for 2034. The optimists believe and hope that maybe it'll go a little bit forward, but usually for space experiments it takes longer, not less. So we have to be patient, but I think in time, and that's why I said we're just barely opening the window. We have, just to finish, I didn't show a couple slides at the end for time, but if we project the future, we'll go to a lower frequency by going in space. This is over tens and then maybe hundreds of years. We'll go to yet lower frequency by the technique that's being used and developed is to measure differences in a big array of radio telescopes that are looking at pulsar signals. Those are very steady signals of spinning neutron stars in our galaxy. And if a gravitational wave at very low frequency goes through, it changes those frequencies. They're like clocks, and the clocks change. If you measure it with an array, you can actually get to even lower frequencies. Why are lower and lower frequencies important? It's important because it goes to earlier and earlier times, or closer and closer to the Big Bang, if you want. And so the dream, finally, is to get to do the equivalent of the cosmic microwave background experiment with gravitational waves themselves. The first thing we can do is to see an effect. If you remember, I think I said that we're limited in what we know about the early universe by the fact that the radiation that comes out, electromagnetic radiation, is absorbed while things are so dense before 400,000 years from the Big Bang. So we all wonder what happened at the beginning. There's huge puzzles like why it's all matter and where's the antimatter and how did it develop at the beginning. That can't be probed very well with electromagnetic radiation because it's absorbed. But with gravitational radiation, you can, in principle, when we develop the instruments, go to yet earlier times. So your question was a good one. First, we'll go in space. Then we have ways to go to yet lower frequency, and hopefully eventually really do what gravitational waves can uniquely do, which is to study something that we all should care about, and that is how it all began, the earliest instance of the universe. It's after my time, but it'll happen, I think.
My question is, why do you think that we are not detecting the amount of expected mergers in the, for example, in the galactic center with gravitational waves?
I heard the question, but I didn't really understand it.
Yeah, sorry. Yeah, because I mean,
it may have been the translation to English, but
I mean, for example, with microlensing, we know that we expect a huge amount of black holes in the galactic center.
So those are okay. So she was asking about detection. If we, I think I understand what you're asking. So let me try, and then if I don't, she rightfully says we detected these black holes, but there's these huge ones at the center of our galaxy. Why aren't we detecting those? And that's simple. That's because of the fact that the black hole, as I showed, even the events that we saw, the heavier the black holes, the lower the frequency. And we can only go down to the frequencies that we can hear on the Earth. And any effects from objects that are really huge are going to be a lower frequency. So we can't detect them. So the problem is ours, not the fact that they don't exist. I mean, it's not a physics problem, it's a detectable problem.
Could gravitational waves be used also to detect dark matter, for example?
There was the question again, to repeat it, is can we possibly understand the puzzle about dark matter from gravitational waves? The answer is I can't give definitively because we don't really know what gravitational wave, what dark matter is. There are conjectures, and most of the dark matter experiments are looking for microscopic kind of matter that's different from the particles that we see. Some people hoped it was the kind of particle looked for at CERN called supersymmetry. An alternate idea that has been proposed is that the black holes that we see actually are primordial, meaning they came from the Big Bang itself, in which case they could be constituted and be part or some of the dark matter itself. We don't know enough about the primary explanation is that they came, like I showed it, from the collapse of stars after the Big Bang. But they could have come primordially, but we don't know and have a good explanation for why we're finding such heavy black holes, because the mechanisms that we're used to for making black holes from the collapse of stars require a very big, heavy star. But big, heavy stars aren't stable. And so we've had to concoct questions of how you made them so stable. So there's three ideas right now for where these black holes came from. One is that they're living in some part of the universe that has what we call low metallicity. That is a part of the universe where elements from outside are not causing it to be so unstable, and heavier stars can exist. I don't know if it's true, that's an idea. The second is that maybe these heavy black holes like we saw, which were not expected by astronomers, come from very dense parts of the universe, dense clusters, in which case they were close enough together that they ate each other up until you got heavy ones. The third idea is that they were actually born primordially, and they came from the early universe, in which case people conjecture that those, if they were that, they could account for some of the dark matter. Some recent observations tend to go against that, but they're not definitive yet, so we'll have to see. But there's a possibility, depending on what black holes are, that this is connected.
So I have a question about the instrumentation and the physics behind that. So we are measuring different interferences at the scale of the millifermi, so 10 to the minus 18 meters. And I was thinking, like, at the scales, it's impossible to not take count of quantum fluctuations of the instruments. So what I was thinking for the future, what are we studying to, what are we thinking to change in order to increase this sensibility in order to account for these quantum fluctuations other than cooling the system?
Yeah. So what was recognized is that we start getting to small enough distances that there are quantum effects in the interferometry itself. And we're well aware of that. We have quantum effects that have to do with the problem experimentally that you hit first. The first quantum effect that we talk about is that as you increase the power of the laser and have more and more photons hitting the mirror, we have a pressure on the mirror. So in one sense, you have more photons, which you want. The other sense, you have a fluctuation because of the pressure on the mirror. And we're not there yet. We have ways to do a little bit better by using different modes of the shape of the light, what's called squeeze light. But eventually, it's a problem, just as you've pointed out. We're just not quite there yet. We're able to go quite a ways, at which point, it's one of the first problems, I think, that is kind of fundamental that we start hitting that limits interferometry that we have to see how to solve. But we're not there yet. It's the kind of a factor of 10 away.
No more question? Okay.
Well, I'm out.
Let's thank again Professor un annuncio, un attimo.
Allora, qua fra voi ci sono dei ricercatori che hanno questa maglietta, che, insomma, bianca con sopra. Sono alcuni dei ricercatori che hanno partecipato alla scoperta delle onde gravitazionali. Potete parlarci. Fuori c'è un caffè, qualche dolcetto che vi aspetta. Insieme a questo vi diamo una penna USB dove abbiamo caricato una serie di documenti divulgativi sulle onde gravitazionali e su altre cose, e vi verrà consegnata insieme a un libricino che descrive il nostro dipartimento. Grazie.